हेलो एवरीवन, वंस अगेन वेलकम बैक टू आवर चैनल बीट द नीट। और आज हम करने जा रहे हैं यूनिट 13 हाइड्रोकार्बन्स। बच्चों, ये सिर्फ एक ऑडियो बुक है, कोई एक्सप्लेनेशन नहीं है, तो इसलिए आप लोग जब इसे सुने तो बी स्पेसिफिक विद दैट। बहुत सारे बच्चे कमेंट सेक्शन में कहते हैं कि मैम आपने एक्सप्लेन क्यों नहीं किया, तो बच्चे इसका टाइटल रीड करिए, दैट इज ओनली एंड ओनली ऑडियो बुक। सो आप सभी से विनम्र निवेदन है कि आप लोग प्लीज इसे ज्यादा से ज्यादा अपने दोस्तों के साथ शेयर करें ताकि उनको भी इसका बेनिफिट मिल सके। और अगर आपको लगता है कि ये ऑडियो बुक्स आपकी रिवीजन में वाकई में हेल्प कर रही हैं, तो यू कैन से थैंक्स टू मी, राइट? प्रेस द लाइक बटन एंड इफ यू आर न्यू ऑन माई चैनल देन प्लीज सब्सक्राइब। चलिए स्टार्ट करते हैं यूनिट 13 हाइड्रोकार्बन्स। Hydrocarbons are the important sources of energy. The term hydrocarbon is self-explanatory, which means compound of carbon and hydrogen only. Hydrocarbons play a key role in our daily life. You must be familiar with the terms Lpg and Cng used as fuels. Lpg is the abbreviated form of liquefied petroleum gas, whereas Cng stands up compressed natural gas. Another term, LNG, liquefied natural gas, is also in news these days. This also a fuel and is obtained by a liquefaction of natural gas. Petrol, diesel and kerosene oil are obtained by the fractional distillation of petroleum found under the earth's crust. Coal gas is obtained by the destructive distillation of coal. Natural gas is found in upper strata during drilling of oil wells. The gas after compression is known as compressed natural gas. LPG is used as a domestic fuel with the least pollution. Kerosene oil is also used as a domestic fuel, but it causes some pollution. Automobiles need fuels like petrol, diesel, and CNG. Petrol and CNG operated automobiles cause less pollution. All these fuels contain mixture of hydrocarbons, which are sources of energy. Hydrocarbons are also used for the manufacture of polymers like polythene, polypropylene, polystyrene, etc. Higher hydrocarbons are used as solvents for paints. They are also used as the starting materials for manufacture of many dyes and drugs. Thus, you can well understand the importance of hydrocarbons in your daily life. In this unit, you will learn more about hydrocarbons. 13.1 Classification. Hydrocarbons are of different types. Depending upon the type of carbon-carbon bonds present, they can be classified into three main categories. Number 1, saturated, number 2, unsaturated, and number 3, aromatic hydrocarbons. Saturated hydrocarbons contain carbon-carbon and carbon-hydrogen single bonds. If different carbon atoms are joined together to form open chain of carbon atoms with single bonds, they are termed as alkanes, as you have already studied in Unit 12. On the other hand, if carbon atoms form a closed chain or a ring, they are termed as cycloalkanes. Unsaturated hydrocarbons contain carbon-carbon multiple bonds, double bonds, triple bonds, or both. Aromatic hydrocarbons are a special type of cyclic compounds. You can construct a large number of models of such molecules of both types, open chain and closed chain, keeping in mind that carbon is tetravalent and hydrogen is monovalent. For making models of alkanes, you can use toothpicks for bonds and plasticine balls for atoms. For alkenes, alkynes, and aromatic hydrocarbons, spring models can be constructed. 13.2 Alkanes. As already mentioned, alkanes are saturated open chain hydrocarbons containing carbon-carbon single bonds. Methane is the first member of this family. Methane is a gas found in coal mines and marshy places. If you replace one hydrogen atom of methane by carbon and join the required number of hydrogen to satisfy the tetravalence of the other carbon atom, what do you get? You get C2H6. This hydrocarbon with molecular formula C2H6 is known as ethane. Thus, you can consider C2H6 as derived from CH4 by replacing one hydrogen atom by CH3 group. Go on constructing alkanes by doing this theoretical exercise, that is replacing hydrogen atom by CH3 group. The next molecules will be C3H8, C4H10 and so on. Here you can see this. These hydrocarbons are inert under normal conditions as they do not react with acid, bases and their other regions. Hence they were earlier known as paraffins. Latin, param, little, and affins means affinity. Can you think of the general formula of alkane family of homologous series? If we examine the formula of different alkanes, we find that the general formula of alkane is CnH2n plus 2. It represents any particular homolog when n is given appropriate value. Can you recall the structure of methane? According to Whisper theory, Unit 4, methane has a tetrahedral structure, figure 13.1, in which carbon atom lies at the center and the 4 hydrogen atoms lie at the 4 corners of a regular tetrahedron. That is, all HCH bond angles are of 109.5 degree. In alkanes, tetrahedra are joined together in which CC and CH bonds lengths are 154 pm and 112 pm respectively. You have already read that CC bond and CH sigma bonds are formed by head-on overlapping of sp3 hybrid orbitals of carbon and 1s orbitals of hydrogen atoms. 13.2.1 Nomenclature and Isomerism. You have already read about nomenclature of different classes of organic compounds in Unit 12. Nomenclature and isomerism in alkanes can further be understood with the help of few more examples. Common names are given in parenthesis. First 3 alkanes, methane, ethane and propane have only one structure, but higher alkanes can have more than one structure. Let us write a structure for C4H10. 4 carbon atoms of C4H10 can be joined either in a continuous chain or with a branch chain in the following 2 ways. You can see here butane, that is N-butane, boiling point is 273 Kelvin. And here is the isobutane, the boiling point is 261 Kelvin. In how many ways you can join 5 carbon atoms and 12 hydrogen atoms of C5H12? They can be arranged in 3 ways as shown in structure 3rd to 5th. You can see here pentane, boiling point 309 Kelvin, isopentane, boiling point 301 Kelvin, and neopentane, boiling point is 282.5 Kelvin. Structures first and second possesses same molecular formula but differ in their boiling points and other properties. Similarly, structure 3rd, 4th and 5th possesses the same molecular formula but have different properties. Structures first and seconds are isomers of butane, whereas structures 3rd, 4th and 5th are isomers of pentane. Since difference in properties is due to the difference in their structures, they are known as structural isomers. It is also clear that structure 1 and 3rd have continuous chain of carbon atoms, but structure 2nd and 4th and 5th have a branched chain. Such structural isomers which differ in chain of carbon atoms are known as chain isomers. Thus, you have seen that C4H10 and C5H12 have 2 and 3 chains isomers respectively. Based upon the number of carbon atoms attached to a carbon atom, the carbon atom is termed as primary, secondary, tertiary and quaternary or quaternary. Carbon atom attached to no other carbon atom as in methane or to only one carbon atom as in ethane is called primary carbon atom. Terminal carbon atoms are always primary. Carbon atom attached to 2 carbon atoms is known as secondary. Tertiary carbon is attached to 3 carbon atoms and neo or quaternary carbon is attached to 4 atoms of carbon. Can you identify primary, secondary, tertiary and quaternary carbon atoms in the structure 1 to 5? If you go on constructing structures for higher alkanes, you will be getting still larger number of isomers. C6H14 has got 5 isomers and C7H16 has 9. As many as 75 isomers are possible for C10H22. In a structure 2nd, 4th and 5th, you observe that CH3 group is attached to carbon atom numbered as 2. You will come across groups like CH3, C2H5, C3H7, etc. attached to carbon atoms in alkanes for other classes of compounds. These groups or substituents are known as alkyl groups as they are derived from alkanes by removal of one hydrogen atom. General formula of alkyl groups is CnH2n plus 1. Let us recall the general rules for nomenclature already discussed in Unit 12. Nomenclature of substituted alkanes can further be understood by considering the following problem. And here you can see table 13.1 nomenclature of few organic compounds. So here you can see all the compounds, their structure and IUPAC name and the remarks. If it is important to write the correct IUPAC name for a given structure, it is equally important to write the correct structure from the given IUPAC name. To do this, first of all, the longest chain of carbon atoms corresponding to the parent alkane is written. Then after numbering it, the substituents are attached to the correct carbon atoms and finally valence of each carbon atom is satisfied by putting the correct number of hydrogen atoms. This can be clarified by writing the structure of 3-ethyl and 2-dimethyl pentane in the following steps. You can see here, first is draw the chain of 5 carbons, then after give number to the carbon atoms, then attach ethyl group at carbon 3 and 2 methyl groups at carbon 2. You can see here. Then after 4th step is satisfying the valence of each carbon atom by putting requisite number of hydrogen atoms. Thus we arrive at the correct structure if you have understood writing of a structure from the given name. attempt the following problems. You can see the problems here. Now 13.2.2 Preparation. Petroleum and natural gas are the main sources of alkanes. However, alkanes can be prepared by following methods. Number 1. From unsaturated hydrocarbons. Dihydrogen gas adds to alkenes and alkynes in the presence of finely divided catalysts like platinum, palladium or nickel to form alkanes. This process is called hydrogenation. These metals absorb dihydrogen gas on their surfaces and activate the hydrogen-hydrogen bond. Platinum and palladium catalyze the reaction at room temperature, but relatively higher temperature and pressure are required with nickel catalyst. You can see the reaction here. Number 2, from alkyl halides. Alkyl halides accept fluorides on reduction with zinc and dilute hydrochloric acid give alkanes. CH3Cl plus H2 in the presence of zinc and H ion, it gives out CH4 plus HCl. And C2H5Cl plus H2 in the presence of zinc and H ion, it gives C2H6 plus HCl. And the same way we will get with 1-chloropropane in the presence of Zn and H ion plus H2 gives out CH3CH2CH3, that is propane plus HCl. Number 2, alkyl halides on treatment with sodium metal in dry ethereal free from moisture solution give higher alkanes. This reaction is known as Wood's reaction and is used for the preparation of higher alkanes containing even number of carbon atoms, that is CH3Br plus 2Na plus BrCH3, and in the presence of dry ether it is forming ethane plus 2NaBr. Same way it is forming the N-butane. What will happen if two different alkyl halides are taken? Number 3, from carboxylic acid. Number 1, sodium salts of carboxylic acids on heating with soda lime, that is mixture of sodium hydroxide and calcium oxide, give alkanes containing one carbon atom less than the carboxylic acid. This process of elimination of carbon dioxide from a carboxylic acid is known as decarboxylation. CH3COO negative Na positive plus NaOH in the presence of CaO, and on heating it gives out CH4 plus Na2CO3, sodium ethanoate. And here you can see this reaction. Number 2, coal-based electrolytic method. An aqueous solution of sodium or potassium salt of carboxylic acid on electrolysis gives alkane containing even number of carbon atoms at the anode. 2CH3COO negative Na positive plus 2H2O, that is the sodium acetate, on electrolysis gives out CH3CH2 plus 2CO2 plus H2 plus 2NaOH. And the reaction is supposed to follow the following path. Here you can see the complete path of the reaction at anode as well as at cathode. Methane cannot be prepared by this method. Why? 13.2.3 Properties. Physical properties. Alkanes are almost non-polar molecules because of the covalent nature of CC and CH bonds and due to very little difference of electronegativity between carbon and hydrogen atoms. They possess weak van der Waals forces. Due to the weak forces, the first four members C1 to C4 are gases, C5 to C17 are liquids, and those containing 18 carbon atoms are solids at 298 Kelvin. They are colorless and odorless. What do you think about solubility of alkanes in water based upon non-polar nature of alkenes? Petrol is a mixture of hydrocarbons and is used as a fuel for automobiles. Petrol and lower fraction of petroleum are also used for dry cleaning of clothes to remove grease stains. On the basis of the observation, what do you think about the nature of the greasy substance? You are correct if you say that grease mixture of higher alkanes is non-polar and hence hydrophobic in nature. It is generally observed that in relation to solubility of substances in solvent, polar substances are soluble in polar solvents, whereas the non-polar ones in non-polar solvents, that is like dissolves like. Boiling point of different alkanes are given in table 13.2, from which it is clear that there is a steady increase in boiling point with increase in molecular mass. This is due to the fact that the intermolecular van der Waals forces increase with increase of the molecular size of the surface area of the molecule. You can make an interesting observation by having a look on the boiling points of three isomeric pentanes, where pentane 2-methylbutane and 2,2-dimethylpropane. It is observed in table 13.2 that pentane having a continuous chain of 5 carbon atoms has the highest boiling point 309.1 Kelvin, whereas 2,2-dimethylpropane boils at 282.5 Kelvin. With increase in number of branch chain, the molecule attains the shape of a sphere. This results in a smaller area of contact and therefore weak intermolecular forces between spherical molecules, which are overcome at relatively lower temperature. Chemical properties, as already mentioned, alkanes are generally inert towards acids, bases, oxidizing, and reducing agents. However, they undergo the following reaction under certain conditions. Number 1, substitution reaction. One or more hydrogen atoms of alkanes can be replaced by halogens, nitro group and sulfonic acid group. Halogenation takes place either at higher temperature, 570 to 773 Kelvin, or in the presence of diffuse sunlight or ultraviolet light. Lower alkanes do not undergo nitration and sulfonation reaction. These reactions in which hydrogen atoms of alkanes are substituted are known as substitution reaction. As an example, chlorination of methane is given below. Halogenation, CH4 plus Cl2 in the presence of HNO, sunlight, that is forming CH3Cl plus HCl, and in the next reaction it is forming the same way dichloromethane, then after trichloromethane and the tetrachloromethane. Here you can see the variation of melting point and boiling point in alkanes. Here you can see the molecular formula, name, molecular mass, boiling point and melting point. The table is here. Here you can see the reaction CH3 plus Cl2 in the presence of HNO. It is forming CH3CH2Cl plus HCl, that is a chloroethane. It is found that the rate of reaction of alkanes with halogen is F2 is greater than Cl2 is greater than Br2 is greater than I2. Rate of replacement of hydrogens of alkanes is tertiary is greater than secondary is greater than primary. Fluorination is too violent to be controlled. Iodination is very slow and a reversible reaction. It can be carried out in the presence of oxidizing agents like HiO3 or HNO3. So here you can see the reaction as CH4 plus I2 reversible CH3I plus HI. HiO3 plus 5HI gives out 3I2 plus 3H2O. Halogenation is supposed to be proceed via free radical chain mechanism involving 3 steps, namely initiation, propagation, and termination as given below. Mechanism number 1, initiation. The reaction is initiated by homolysis of chlorine molecule in the presence of light or heat. The chlorine-chlorine bond is weaker than the CC and CH bond and hence is easiest to break. Cl, single bond Cl, and on homolysis it is forming the chlorine free radicals. Number 2, propagation. Chlorine free radical attacks the methane molecule and takes the reaction in the forward direction by breaking the CH bond to generate methyl free radical with the formation of HCl. Here you can see this reaction. The methyl radical thus obtained attacks the second molecule of chlorine to form CH3Cl with the liberation of another chlorine free radical by homolysis of chlorine molecule. Here you can see the next reaction and its description is here. The chlorine and methyl free radicals generated above repeat steps A and B respectively and thereby set up a chain of reaction. The propagation step A and B are those which directly give principal products, but many other propagation steps are possible and may occur. 2 such steps given below explain how more highly halogenated products are formed. CH3Cl plus free radical chlorine and it is forming CH2Cl and HCl, and then after next reaction you can see here. The third step is termination. The reaction stops after some time due to consumption of reactants and or due to the following side reactions. The possible chain terminating steps, you can see all these steps A, B and C. Though in CH3Cl the one of the product is formed but free radicals are consumed and the chain is terminated. The above mechanism helps us to understand the reason of the formation of ethane as a byproduct during chlorination of methane. Number 2, combustion. Alkanes on heating in the presence of air or dioxygen are completely oxidized to carbon dioxide and water with the evolution of large amount of heat. Here is the CH4 plus 2O2 gives out CO2 plus 2H2O and the delta H value is here minus 890 kilojoule per mole. And next reaction is a C4H10 plus 13 by 2O2 gives out 4 CO2 plus 5 H2O and delta H value is minus 2875.84 kilojoule per mole. The general combustion equation for any alkane is CnH2n plus 2 plus 3n plus 1 by 2O2 gives out NCO2 plus n plus 1 H2O. Due to the evolution of large amount of heat during combustion, alkanes are used as fuels. During incomplete combustion of alkanes with insufficient amount of air or dioxygen, carbon black is formed, which is used in the manufacture of ink, printer ink, black pigments, and as filters. CH4 plus O2, on incomplete combustion, it is forming C plus 2H2O. Controlled oxidation. Alkanes on heating with a regulated supply of dioxygen or air at high pressure and in the presence of suitable catalyst give a variety of oxidation products. Reaction is 2CH4 plus O2 in the presence of Cu at 523 Kelvin and 100 atmospheric pressure. It is forming methanol. Second reaction is CH4 plus O2 in the presence of MO2O3 and on heating it is forming HCHO, that is methanol plus H2O. Third reaction is 2CH3CH3 plus 3O2, and it is forming on heating and in the presence of CH3CO whole twice Mn ethanoic acid plus 2H2O. Number 4, ordinarily alkanes resist oxidation, but alkanes having tertiary hydrogen atom can be oxidized to corresponding alcohols by potassium permanganate. And reaction is CH3 whole thrice CH in the presence of KMNO4. On oxidation, it is forming CH3 whole thrice COH. That is 2-methylpropane is forming 2-methylpropane 2-ol. Fourth, isomerization. N-alkanes on heating in the presence of anhydrous aluminum chloride and hydrogen chloride gas isomerize to branch chain alkanes. Major products are given below. Some minor products are also possible which you can think over. Minor products are generally not reported in organic reactions. Here you can see this reaction. Number 5, aromatization. N-alkanes having 6 or more carbon atoms on heating at 773 Kelvin at 10 to 20 atmospheric pressure in the presence of oxides of vanadium, molybdenum or chromium supported over alumina get dehydrogenated and cyclized to benzene and its homologous. This reaction is known as aromatization or reforming. Here you can see this reaction. Toluene C7H8 is methyl derivative of benzene. Which alkane do you suggest for preparation of toluene? Number 6, reaction with steam. Methane reacts with steam at 1273 Kelvin in the presence of nickel catalyst to form carbon monoxide and dihydrogen. This method is used for industrial preparation of dihydrogen gas. CH4 plus H2O gives out CO plus 3H2 in the presence of nickel and on heating. Number 7, pyrolysis. Higher alkanes on heating to higher temperature decompose into lower alkanes, alkenes, etc. Such a decomposition reaction into smaller fragments by the application of heat is called pyrolysis or cracking. Here you can see the reaction of C6H14 at 773 K, and it is forming these products. Pyrolysis of alkanes is believed to be a free radical reaction. Preparation of oil gas or petrol gas from kerosene oil or petrol involves the principle of pyrolysis. For example, dodecane, a constituent of kerosene oil on heating to 973 Kelvin in the presence of platinum, palladium or nickel gives a mixture of heptane and pentene. C12H26 gives out C7H16 plus C5H10 plus other products in the presence of platinum, palladium and nickel at 973 Kelvin. 13.2.4 Conformations. Alkanes contain carbon-carbon sigma bonds. Electron distribution of the sigma molecular orbital is symmetrical around the internuclear axis of CC bond, which is not disturbed due to the rotation about its axis. This permits free rotation about CC single bond. This rotation results into different spatial arrangements of atoms in space which can change into one another. Such a spatial arrangement of atoms which can be converted into one another by rotation around CC single bond are called conformations or conformers or rotamers. Alkanes can thus have infinite number of conformations by rotation around CC single bonds. However, it may be remembered that rotation around a CC single bond is not completely free. It is hindered by a small energy barrier of 1 to 20 kJ per mole. Due to weak repulsive interactions between the adjacent bonds, such a type of repulsive interaction is called torsional strain. Conformations of ethane. Ethane molecule C2H6 contains a carbon-carbon single bond with each carbon atom attached to 3 hydrogen atoms. Considering the ball and stick model of ethane, keep one carbon atom stationary and rotate the other carbon atom around the CC axis. This rotation results into infinite number of spatial arrangements of hydrogen atoms attached to one carbon atom with respect to the hydrogen atoms attached to the other carbon atom. These are called conformational isomers, conformers. Thus, there are infinite number of conformations of ethane. However, there are two extreme cases. One such conformation in which hydrogen atoms attached to two carbons are as close together as possible is called eclipsed conformation, and the other in which hydrogens are as far apart as possible is known as the staggered conformation. Any other intermediate conformations is called a skew conformation. It may be remembered that in all the conformations, the bond angles and the bond length remain the same. Eclipsed and the staggered conformations can be represented by Sawhorse and Newman projections. Number 1, Sawhorse projections. In this projection, the molecule is viewed along the molecular axis. It is then projected on paper by drawing the central CC bond as a somewhat longer straight line. Upper end of the line is slightly tilted towards right or left hand side. The front carbon is shown at the lower end of the line, whereas the rear carbon is shown at the upper end. Each carbon has 3 lines attached to it corresponding to 3 hydrogen atoms. The lines are inclined at an angle of 120 degrees to each other. Sawhorse projections of eclipsed and staggered conformations of ethane are depicted in figure 13.2. You can see here. Number 2, Newman projections. In this projection, the molecule is viewed at the CC bond head on. The carbon atom nearer the eye is represented by a point. 3 hydrogen atoms attached to the front carbon atom are shown by 3 lines drawn at an angle of 120 degrees to each other. The rear carbon atom, the carbon atom away from the eye, is represented by a circle, and the 3 hydrogen atoms are shown attached to it by shorter lines drawn at angle of 120 degrees to each other. The Newman's projections are depicted in figure 13.3. You can see here. Relative stability of conformations. As mentioned earlier, in staggered form of ethane, the electron clouds of carbon-hydrogen bonds are as far apart as possible. Thus, there are minimum repulsive forces, minimum energy, and maximum stability of the molecule. On the other hand, when the staggered form changes into eclipsed form, the electron clouds of the carbon-hydrogen bonds come closer to each other, resulting in increase in electron cloud repulsion. To check the increased repulsive forces, molecule will have to possess more energy and thus has lesser stability. As already mentioned, the repulsive interaction between the electron clouds, which affects the stability of a conformation, is called torsional strain. Magnitude of torsional strain depends upon the angle of rotation about CC bond. This angle is also called dihedral angle. Of all the conformations of ethane, the staggered form has the least torsion strain and the eclipsed form the maximum torsional strain. Therefore, staggered conformation is more stable than the eclipsed conformation. Hence, molecule largely remains in staggered conformation, or we can say that it is preferred conformation. And thus it is may be inferred that rotation around CC bond in ethane is not completely free. The energy difference between two extreme forms is of the order 1 to 0.5 kJ per mole, which is very small. Even at ordinary temperature, the ethane molecules gains thermal or kinetic energy sufficient enough to overcome this energy barrier of 12.5 kJ per mole through intermolecular collisions. Thus, it can be said that rotation about carbon-carbon single bond in ethane is almost free for all practical purposes. It has not been possible to separate and isolate different conformational isomers of ethane. 13.3 Alkenes. Alkenes are unsaturated hydrocarbons containing at least one double bond. What should be the general formula of alkenes? If there is one double bond between two carbon atoms in alkenes, they must possess two hydrogen atoms less than alkanes. Hence, general formula for alkenes is CnH2n. Alkenes are also known as olefins, oil forming it is, since the first member ethylene or ethene C2H4 was found to form an oily liquid on reaction with chlorine. 13.3.1 Structure of double bond. Carbon-carbon double bond in alkenes consists of one strong sigma bond, and that bond enthalpy is about 397 kJ per mole due to head-on overlapping of sp2 hybridized orbitals, and one weak pi bond. That bond enthalpy is about 284 kJ per mole, obtained by lateral or sideways overlapping of the two 2p orbitals of the two carbon atoms. The double bond is shorter in bond length than the CC single bond, 154 pm. You have already read that the pi bond is a weaker bond due to poor sideways overlapping between the two 2p orbitals. Thus, the presence of the pi bond makes alkenes behave as sources of loosely held mobile electron. Therefore, alkenes are easily attacked by reagents or compounds which are in search of electrons. Such reagents are called electrophilic reagents. The presence of weaker pi bond makes alkenes unstable molecules in comparison to alkanes, and thus alkenes can be changed into single bond compounds by combining with the electrophilic reagents. Strength of the double bond enthalpy 681 kJ per mole is greater than that of carbon-carbon single bond in ethane, that is bond enthalpy is 348 kJ per mole. Orbital diagram of ethene molecule are shown in figure 13.4 and 13.5. See here the diagram. 13.3.2 Nomenclature. For nomenclature of alkenes in IUPAC system, the longest chain of carbon atoms containing the double bond is selected. Numbering of the chain is done from the end which is nearer to the double bond, The suffix "ene" replaces "ane" of alkanes. It may be remembered that the first member of alkene series is CH2, replacing N by 1 and CnH2n, known as methane, but has a very short life. As already mentioned, first stable member of alkene series is C2H4, known as ethylene, common or ethene IUPAC. IUPAC name of a few members of alkenes you can see here: propene, but1-ene, but2-ene, buta 1,3, diene, 2-methyl-prop-1-ene, and 3-methyl-but1-ene. See this problem. 13.3.3 Isomerism. Alkenes show both structural isomerism and geometrical isomerism. Structural isomerism, as in alkanes, ethene C2H4 and propene C3H6 can have only one structure, but alkenes higher than propene have different structures. Alkene possessing C4H8 as molecular formula can be written in the following three ways. You can see all the ways: number 1, number 2, and number 3. Structures 1 and 3rd and 2nd and 3rd are the examples of chain isomerism, whereas structure 1 and 2nd are the position isomers. Geometrical isomerism. Doubly bonded carbon atoms have to satisfy the remaining two valences by joining with two atoms or groups. If two atoms or groups attached to each carbon atom are different, they can be represented, and here it can be represented in space in the following two ways. Here you can see all the ways, A and B. In A, the two identical atoms, that is both the X or both the Y, lie on the same side of the double bond, but in B, the two X or two Y lie across the double bond or on the opposite sides of the double bond. This results in the different geometry of A and B, that is, deposition of atoms or groups in space in the two arrangements is different. Therefore, they are stereoisomers. They would have the same geometry if atoms or groups around CC bond can be rotated, but rotation around CC bond is not free. It is restricted. For understanding this concept, take two pieces of strong cardboards and join them with the help of two nails. Hold one cardboard in your one hand and try to rotate the other. Can you really rotate the other cardboard? The answer is no. The rotation is restricted. This illustrates that the restricted rotation of atoms or groups around the doubly bonded carbon atoms give rise to different geometries of such compounds. The stereoisomers of this type are called geometrical isomers. The isomer of the type A, in which two identical atoms or groups lie on the same side of the double bond, is called cis isomer, and the other isomer of the type B, in which identical atoms or groups lie on the opposite sides of the double bond, is called trans isomer. Thus, cis and trans isomers have the same structure but have different configuration, that is, arrangement of atoms or groups in space. Due to different arrangement of atoms or groups in space, these isomers differ in their properties like melting point, boiling point, dipole moment, solubility, etc. Geometrical or cis-trans isomers of but2-ene are represented below. Here you can see but2-ene, the boiling point is 277 Kelvin, and but2-ene, this structure trans 1, and its boiling point is 274 Kelvin. Cis form of alkene is found to be more polar than the trans form. For example, dipole moment of cis but2-ene is 0.33 d by, and whereas the dipole moment of the trans is almost zero, or it can be said that trans but2-ene is non-polar. This can be understood by drawing geometries of the two forms as given below, from which it is clear in the trans but2-ene the two methyl groups are in opposite directions. Therefore, dipole moments of CCH3 bonds cancel, thus making the trans form non-polar. You can see both structures. In the case of solids, it is observed that the trans isomer has higher melting point than the cis form. Geometrical or cis-trans isomers is also shown by alkenes of the types XYC is double bond CXZ and XYC double bond CZW. 13.3.4 Preparation. Number 1, from alkynes. Alkynes on partial reduction with calculated amount of dihydrogen in the presence of palladized charcoal partially deactivated with poisons like sulfur compounds or quinoline give alkenes. Partially deactivated palladized charcoal is known as Lindlar's catalyst. Alkenes thus obtained are having cis geometry. However, alkynes on reduction with sodium and liquid ammonia form trans alkenes. You can see these reactions. Will propene thus obtained show geometrical isomerism? Think for the reason in support of your answer. Number 2, from alkyl halides. Alkyl halides Rx on heating with alcoholic potash, that is potassium hydroxide dissolved in alcohol, say ethanol, eliminate one molecule of halogen acid to form alkenes. This reaction is known as dehydrohalogenation, that is removal of halogen acid. This is example of beta elimination reaction. Since hydrogen atom is eliminated from the beta carbon atom next to the carbon to which halogen is attached. You can see here. Nature of halogen atom and the alkyl group determine rate of reaction. It is observed that for halogens the rate is iodine is greater than bromine, is greater than chlorine, while for alkyl groups it is tertiary, is greater than secondary, is greater than primary. Number third, from vicinal dihalides. Dihalides in which two halogen atoms are attached to two adjacent carbon atoms are known as vicinal dihalides. Vicinal dihalides on treatment with zinc metal lose a molecule of ZnX2 to form an alkene. This reaction is known as dehalogenation. CH2Br, CH2Br plus Zn gives out CH2 double bond CH2 plus ZnBr2. CH3CHBr, CH2Br plus Zn gives out CH3CH double bond CH2 plus ZnBr. From alcohols by acidic dehydration. You have read during nomenclature of different homologous series in Unit 12 that alcohols are the hydroxy derivatives of alkanes. They are represented by ROH, where R is CnH2n plus 1. Alcohols on heating with concentrated sulfuric acid form alkenes with the elimination of one water molecule. Since a water molecule is eliminated from the alcohol molecule in the presence of an acid, this reaction is known as acidic dehydration of alcohols. This reaction is also the example of beta elimination reaction since OH group takes out one hydrogen atom from the beta carbon atom. You can see this reaction here. 13.3.5 Properties. Physical properties. Alkenes as a class resemble alkanes in physical properties except in types of isomerism and difference in polar nature. The first three members are gases, the next 14 are liquids, and the higher ones are solids. Ethene is a colorless gas with a faint sweet smell. All other alkenes are colorless and odorless, insoluble in water but fairly soluble in non-polar solvents like benzene, petroleum, ether. They show a regular increase in boiling point with increase in size, that is every CH2 group added increases boiling point by 20 to 30 Kelvin. Like alkanes, straight chain alkenes have higher boiling point than isomeric branch chain compounds. Chemical properties. Alkenes are the rich source of loosely held pi electrons due to which they show addition reaction in which the electrophiles add on the carbon-carbon double bond to form the addition products. Some reagents also add by free radical mechanism. There are cases when under special conditions alkenes also undergo free radical substitution reaction. Oxidation and ozonolysis reactions are also quite prominent in alkenes. A brief description of different reactions of alkenes is given below. Number 1, addition of dihydrogen. Alkenes add up one molecule of dihydrogen gas in the presence of finely divided nickel, palladium or platinum to form alkanes. Number 2, addition of halogens. Halogens like bromine or chlorine add up to alkene to form vicinal dihalides. However, iodine does not show addition reaction under normal condition. The reddish-orange color of bromine solution in carbon tetrachloride is discharged when bromine adds up to an unsaturation site. This reaction is used as a test for unsaturation. Addition of halogens to alkenes is example of electrophilic addition reaction involving cyclic halonium ion formation, which you will study in higher class. You can see these two reactions here. Number 3, addition of hydrogen halides. Hydrogen halides HCl, HBr, Hi add up to alkenes to form alkyl halides. The order of reactivity of the hydrogen halide is Hi greater than HBr is greater than HCl. Like addition of halogens to alkenes, addition of hydrogen halide is also an example of electrophilic addition reaction. Let us illustrate this by taking addition of HBr to symmetrical and unsymmetrical alkenes. Addition reaction of HBr to symmetrical alkenes. Addition reactions of HBr to symmetrical alkenes, that is similar groups attached to double bond, take place of electrophilic addition mechanism. Here is the reaction CH2 double bond CH2 plus HBr gives out CH3 CH2 Br, and the next reaction you can see here. Addition reaction of HBr to unsymmetrical alkenes, that is Marconikov Rule. And how will HBr add to propene? The two possible products are first and second. You can see the two possible products, that is 2 bromopropane and 1 bromopropane. Marconikov, a Russian chemist, made a generalization in 1869 after studying such reaction in detail. These generalization led Marconikov to frame a rule called Marconikov Rule. The rule states that negative part of the Addendum, adding molecules, that is, gets attached to that carbon atom which possesses lesser number of hydrogen atoms. Thus, according to this rule, product 1, that is 2-bromopropane, is expected. In actual practice, this is the principal product of the reaction. This generalization of Marconikov rule can be better understood in terms of mechanism of the reaction. Mechanism. Hydrogen bromide provides an electrophile H-ion which attacks the double bond to form carbocation as shown below. Here you can see the reaction. A is less stable, B is more stable. So A is here primary carbocation which is less stable, and B is here secondary carbocation which is more stable. Number 1, the secondary carbocation B is more stable than the primary carbocation, therefore the former predominates because it is formed at a faster rate. Number 2, the carbocation B is attacked by bromine negative ion to form the product as follows. Here you can see this reaction. Rest of the part I will record in the second part. So till then revise up to here and then after soon I will upload the second part of this. बच्चा अगर ये वीडियो आपकी हेल्प कर रहा हो, ये ऑडियो बुक्स आपके रिवीजन में हेल्प करती हो तो प्लीज 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 इसको लाइक करिएगा, और अगर चैनल पे आप नए हैं तो सब्सक्राइब करिएगा और इसको अपने दोस्तों के साथ शेयर करना मत भूलिएगा. Take care everyone. Bye bye. See you soon in my next video. Till then, just stay tuned with me. Bye bye.